Yes, we are here to speak about the future of mechanical, but let me start with saying that there is something wrong in the current mechanical design software. Yesterday, Eric mentioned that there are over 12 million of registered AutoCAD users, while the total user base of DWG-based software is probably around 70 million. And many of them do mechanical design. And of course, it's not possible to do mechanical design using basic AutoCAD possibilities. Because what is a mechanical design software? It's a software which allows you to design 3D parts with complex features like holes, like ribs, like pockets. It should be parametric, it should be editable. You should be able to assemble these parts together. You should be able to analyze kinematics of your mechanism. You should be able to compute mass properties to generate bill of materials, to generate drawings, technical drawings, and annotate them according to international standards. And of course, because almost every mechanical assembly contains sheet metal parts. So mechanical design software should support sheet metal design as well. So AutoCAD is not a choice. But what is a choice? In fact, if you look at the proposal for DWG users in mechanical, we can see that all this proposal is wrong. AutoCAD Mechanical is not a choice because it's not a tool to do mechanical design. It's just a tool set to create 2D drawings. You can define product structure, and then you can draw every view manually. You cannot compute mass properties, you cannot analyze, check collisions, make finite elements analysis, and so on, because it's not 3D. Okay, maybe then Inventor? I think no. For DWG users, it's not the choice again, because if you switch to Inventor, you lose your familiar AutoCAD environment. You will lose all customization, all Lisp scripts, all vertical applications, all known tools. And moreover, if you switch to Inventor, you have to change your mind, because behind Inventor there is a very complex design paradigm called history-based modeling. And when you use history-based modeling, you have to always remember how your geometry will be regenerated upon parameter change. So instead of focusing on the usability and manufacturability aspects of your product, you have to think about how geometry will be regenerated, which is stupid. Inventor forces you to be a rather programmer than designer, than design engineer. And of course, Inventor is not a choice because it's impossible to edit existing 3D DWG files with it, because they do not contain design history, do not contain features, so Inventor is not a choice. Then maybe you think that Fusion is a choice. No, because again, it's not AutoCAD-based product. You will lose your customization. Yes, it contains some direct editing tools which allows you to edit geometry without design history, but if you need parameterization, but you need it when you design complex products, in Fusion, you can find only history-based parameterization, the same as in Inventor, because they use the same engine, basically. And one more thing interesting, that you can use Fusion only if you have a stable internet connection. I don't know how many of you have this, because there can be breakdown, of course, always, and with Fusion, you have to stop your work, you have to, because everything you create is stored in the cloud. So I believe all this proposal is wrong. It's not for mechanical design for DWG user. It's not appropriate choice of mechanical design tool for DWG users. What is the right choice? Let me list. First of all, of course, the right mechanical design software for DWG users should be AutoCAD compatible. It should contain all familiar tools on the board. It should support Lisp and .NET and C++ API. It should allow you to run vertical application and so on. Also, it should be fully blown 3D, of course, not 2D. You should design parts, assemblies, sheet metal in 3D, and you should generate drawing views from 3D models, not draw them manually. It should be easy to learn, intuitive and powerful. Easy to learn means that it should be familiar to you. Even before you start to use it, you already know a significant part of this software. And of course, it's very important to edit any existing DWG geometry, 3D solid geometry, but also any imported 3D geometry, because there are a lot of 3D mechanical design software available on the market, and if you collaborate, and you cannot avoid collaboration with your suppliers, partners, they will definitely use some other software like SolidWorks, Solid Edge, CATIA, Creo, and so on. And you have to be able not only exchange data with them, but also to edit imported geometry. That's very important. And also, you should not get in a history-based trap for parametric modeling. You can apply parameterization only when you need and only on limited features of your model. You should not parameterize everything as history-based software does, and so you are in trap and you are very limited in capabilities. Of course, the software should be affordable, should have perpetual license and be available on desktop without any internet connection. And now we are very close to start our live demo, but just before that, let me give you 4 main reasons why BricsCAD Mechanical is your best choice for 3D mechanical design. First of all, it allows you to model freely. You can design in 3D as easy as you draw in 2D. The same creation, modification, and moving tools. And it doesn't matter how your model was designed, with BricsCAD, with SolidWorks, with Inventor, and so on. Of course, because any DWG-based software is oriented on 2D drawings, we have best workflow to create very high-quality mechanical drawings. You can easily turn your design into a set of production drawings. And you can use any data with BricsCAD. You can import from most popular MCAD formats, such as SolidWorks, Creo, CATIA, and so on. You can not only import, but what is the most important, to edit imported geometry. And there is parametric possibilities. You can use existing library of parametric standard parts. We have over 800 types of different bolts, nuts, screws, bearings, and so on. Or you can build your own parametric component using our parameterization technology. And now, let me present, how to say, the main hero of our session. This is the model, 3D model of the excavator. We created in BricsCAD from scratch till the last bolt and nut. We assembled all parts together. They are parametric. We modeled all kinematic joints. And this movie was recorded using BricsCAD AnyPath tool, which was extended in version 19 with the possibility to make parametric animation. In a couple of seconds, you will see this excavator will start to move. And this movement is driven by parameter. We specified connections using expressions. We specified links between different parameters, and it allows us to model that. In fact, we modeled everything, including, for example, this planetary gear joint. So it's possible with BricsCAD with no problem. Of course, we also modeled the main purpose of this excavator. It should move its boom and bucket and made its job, and of course, this is also possible. This is modeled. Okay, the rest of our session will be just live demo of different aspects of BricsCAD Mechanical product. We are going to start with showing you some possibilities of direct and parametric modeling in BricsCAD. And to do that, I'm inviting on the stage my colleague, Alexey Kazakov, who will show you, with the help of another my colleague, Ilya Tadarnikov, how easily it can be done in BricsCAD Mechanical.
Okay. Well, Dmitry, thank you for introducing me. Together with my colleagues and Dmitry, I was involved in development of parametric toolset and direct modeling toolsets from the very beginning. And now I'm really happy to see how the area of applications of these tools extends. And but now we're going to focus with Ilya on demonstration how parametric design, 3D constraints, and direct modeling can be applied in mechanical design context. So let's turn back to our model of excavator and assume as an excavator manufacturer we're going to create a customized version of this model for one of our clients who is target to use it for, say, for trenches digging. This target requires replacing the bucket model with a more narrower version than the one currently installed. And we will show how direct modeling can be applied to customize, to change this bucket. Let's start changing it, and we start from original model we received from in SolidWorks format. We import it using our communicator product, and now we will use direct modeling toolset to change it. Direct modeling assumes that designer interacts with the model using the selection and direct manipulating of faces. So that's why selection tools are very important. Here, Ilya started with the assembly model, and to make it editable, we have to explode one of the components to get 3D solids. So this black bucket model, bucket solids, will now be changed. Here you see this important selection tool when you can specify your view and set your view correctly and use window selection to select precisely the number of faces and solids you need. And afterwards, using manipulator object, we just displace it, the faces on the required distance. That's how this object can be changed and how bucket can be made more narrow. Additional modifications that we are showing now is extension of the stiffness of the top of the bucket to make it more strengthful. And this is done using extrusion, and while extruding you can type the values or use snapping, whatever you need. All the power of all the regular tools are also here. So that's how we made it, how we created more narrow trenches digging version of our bucket. And now another thing, let's assume that we gonna use it bucket, or our client gonna use this bucket in the conditions where a lot of rocks met in the soil, in the ground. And that's why we need to customize one of the tools, or we better call it tooth crown, as we're in UK. So that's tooth crown, we're gonna customize it, and we're gonna change it to make it of very specific form. So first we extract the profile of one of the side faces and to start from, and hide original object to do not obscure the view. Using this profile, we using native extrusion command, regular extrusion, we create the basic shape of the back of the tooth crown, and then there is another selection tool which is quite useful especially when working with imported geometry. It allows you to select and remove fillets of specific radius. This is what Ilya just did, and removing fillets is quite important because otherwise their presence can complicate the direct modeling. Well, now we are changing angle to get required shape of the model, and this is something very basic, and you in fact cannot do too much with such shape because it just do not have enough faces. And we found one of the way to make it more flexible, to introduce more faces to this object, is to make imprinting of the copy of back face, which you can just imprint on this model, and imprinting gives you additional edges that you can, and faces that you can use to reshape this object. After this copies of back face are imprinted, regular push-pull command can be applied, and the shape of the tooth crown can be changed as we need. Also, these additional faces can be rotated a bit to get required form. Well, okay. So next we will show how. Next thing that required by our design is introducing of additional protrusion feature, which can be easily created using rectangle command and combined with dynamical UCS detection. So as soon as you start drawing the rectangle, system automatically selects the face of a solid which is under the cursor, which allows you to create the rectangle easily and fast. And as well as before, while creating the rectangle, all snapping are also available, and this makes it very familiar to regular DWG users who already knows which snapping mode exists, how to use, for example, tracking lines, etc., how to use regular drafting commands. Well, after this extrusion is created, side faces can be rotated using quad tool and specifying the required rotation angle. Well, so now we created this protrusion feature, and what is interesting, there is another selection tool which allows you to select protrusion just in one click. You select it from quad, and after these faces are selected, what is, to me maybe looks as one of the most interesting features we recently introduced. It's a possibility to copy a feature of a 3D solid from one place to another. So this is what you are doing, and Ilya is doing now. That's positioning a copy of this protrusion feature on another side. Well, and now some final modifications. And what remains is to add the mounting opening on the back side of the tooth crown to be able to fix it on the original adapter of the bucket and have the complete design. For this, Ilya already used the depression selection tool, which automatically selected the faces of the opening and manually added the selection of hole faces, and just copied this opening to our new version of the tooth. So, well, now it's time to save this new model and under new name and update the assembly or update the parts on the assembly level to see how it impacts the final design. So here we use replacement using mechanical browser, use replacement command, which allows replacing the tooth to its new version, which we assume more fit for rocky environments. And one final step is updating and replacing the model, the bucket part, the bucket subassembly on the assembly level of the excavator. Well, yes, for do this we use replacement. Something we have to find the correct version, right, Ilya? Okay, so we are done now. Something went a bit wrong. Oh no, that's fine. Yes, that's correct. Well, I looking at the screen on the certain angle, so it looked to me that something is not correct. But yes, it's what we designed. This is what we did. Well, so this is what about direct modeling when you manipulate the faces and object directly using different selection tools, using the native drafting commands, extrusion commands, and manipulator, for example. Well, now what about parametric design? Parametric design is a paradigm when designer controls the geometry using several numerical parameters. To show, in BricsCAD we implement this link between parameters and geometry using different driving objects like, for example, 3D constraints and associative arrays, and using these tools in BricsCAD, it's possible to create what we call parametric components. And what we're going to show, how to create one of the examples of such parametric components, and we selected this oil filter lead assembly to show how to create this parametric object from scratch. Let's design one of the one of the flanges of this oil filter assembly, which oil filter lead assembly, which is normally controlled by a number of parameters like internal diameter, external diameter, and thickness. Let's start designing from the stage when these parameters are already defined on the level of assembly and have some initial values, and let's see how we can link these parameters with geometry. Generally, it doesn't matter in BricsCAD. Either you create this geometry from scratch, either you imported it. The parameters can be attached using 3D constraints just by selecting the corresponding faces of the 3D solid object in such a way that then the parameter of constraint starts to move these faces as soon as parameter is changed. Well, this is how constraints are created manually. You have seen that there is already automated parameterization tool, which which was used yesterday in BIM. As a homework, you can try on such model what it creates. That's more or less what we need. But here we show it how to create constraints manually only for those faces which are involved. So here Ilya controls internal radius with radius constraint and thickness with additional distance constraint. Well, this is how we created the parametric washer-like object. And what remains to complete design of this part is that we need to position holes. On the left, let me introduce, maybe once again in mechanical context, the components panel, which now in V19 includes mostly used standard mechanical holes, which are also internally represented as parametric components controlled by 3D constraints with a specific property that these components are subtracted from the host solid on which they are inserted. These parametric components, these holes also have parameters which can be aligned with using mechanical browser with the parameters of assembly to control the depth of the hole to make it corresponding to the thickness of this flange or washer. And another sort of parameters, as you just seen, it's a number of holes, but it's completely different and it is not controlled by 3D constraints. We control it with associative arrays, and this is also a new feature of BricsCAD V19 when you can combine associative arrays, like in this case polar array, with parametric components. So it's still, when component is put inside parametric array, it is still its parameters still exposed to on the higher level, on the level of your drawing, and you can control either as array parameters using mechanical browser, as you can control them as well as parameters of each hole. Well, this is what we did, and using the animate command, you can see which parameters now can be controlled. Well, and okay, Ilya, let's also change the number of holes to see how it, please. Yes, now we have 6 holes. If you make it 10, that system automatically recomputes the number of the geometry. Well, that's simple, but that's already can represent some standard part which you can use in your designs across your assemblies. And there is also a new feature in BricsCAD that allows what? Yes, which allows to store this component in a convenient place for for later accessing it easily. And this is again the components panel. Using specific create component tool, you just select the solid and store it in the components library as a standard part, and it allows you later to incorporate this drawing, this model to the assemblies once again. So you can see that it appears, this flange model appeared as a icon in the components panel. We can also have a look how easily you can use it just by drag and drop it to the new model. And so this is how the standard library, the components library, can be extended by your own parametric designs. Well, let's return back to the original assembly. So this is already an assembly which contains our part. We created it in advance. Original assembly which creates 2 flanges and the intermediate washer. And this is fully parametric. You can control all the diameters, number of holes, and all these dimensions. Well, but it's incomplete because it doesn't have the standard hardware inserted. The bolts are missed, and they missed on purpose because we wanted to show you the reworked again the subset of components library which is shipped together with BricsCAD V19, and this is a library, full library, reworked library of our standard parts, which now completely parametric. They can be controlled parametrically after insertion. Previously, you could only change the parameter of standard hardware in the moment of insertion, and also they are real parametric components, which means that they can be combined with associative arrays. This is what is now possible. Additional polar array is created, which is creates repetitions, the copies of the standard hardware of the bolts to get the complete assembly. Well, so we are close to have this assembly complete. Ilya now just sets the parameters of newly created array using mechanical browser. And now what's worth to note is that in reality, in manufacturing, due to cost effectiveness requirements and due to manufacturing restrictions, you do not have arbitrary radiuses or diameters for such sort of things. You can only use in your designs only certain combinations of the dimensions of such objects, and usually such configurations is referred as is referred with some part number associated with part number, and very often it's as here this part number and configurations are defined in the Excel spreadsheet, which we can now attach to the geometry using the what we call design table tool. We associate this, and as soon as design table is associated with our parameters, new parameter appears in the mechanical browser, which controls all the dimensions of this part on it. And to change the dimension of this part, one can just choose from drop-down list the corresponding value of this configuration, and system automatically recomputes the geometry. So this is how spreadsheets can be used in BricsCAD to provide specific configurations. Well, so we are close to the end. We just seen how constraints give you freedom to design only once and then generate all the required configurations very fast and easy. So thank you. That's what we wanted to show about direct modeling and parametric design with 3D constraints and associative arrays. And now I give word back to Dmitry, who will show you even more amazing stuff. Thank you very much. Thank you.
Thank you, Alexei. You're probably aware that designing is just one part, important of course, but just one part of mechanical design software. Another important part is the possibility to analyze your design before it goes to production. You have to analyze kinematics, you have to compute mass properties to see center of gravity, to make probably finite element analysis and so on. And now we are going to show you in brief some possibilities for kinematics analysis in BricsCAD. Of course, when you design such things as excavator, you are interested to see how your bucket can be moved. And it can be done with move command in BricsCAD with move tool. But you see that if we start to move it, oops, our boom started to move as well. That's because we forgot, but we did it intentionally, of course. We forgot to create an assembly joint between the boom and the upper platform. It can be easily done by creation of concentric constraint between cylindrical faces of the hole on the boom and the pin on the platform. And if we do that, we will see how can we model the kinematics. Of course, the same concentric constraint exists between the boom and the stick and between stick and the bucket. And now, if we will move the bucket, you will see that the full mechanism is moved, and you can analyze this. What we are watching now is called inverse kinematics, and we do it in real time in BricsCAD. So you can check collision, you can check availability of your bucket and make some design changes if needed, and so on. But of course, in reality, the movement of every element of this boom is driven by hydraulic cylinders. Inside every cylinder there is a piston, and when the piston goes outside of the cylinder, it forces the connected part to move. And let's see how easily we can model it in BricsCAD. First of all, we have to make our piston, we have to convert them to parametric components. To do that, we create a distance constraint between two cylindrical faces on both ends of this cylinder. But for the user, this distance has no meaning. For the user, what is important to measure is the offset of the piston, the value which the piston goes outside of the cylinder. And we can specify this parameter offset, and we can say that the distance is equal to its current value plus offset. And now, if we change the offset value, we will see that the piston will be moved. And before saving this model, we can animate it to see that, yes, it works. Now we can save it, and we are going to update our excavator model. And with this update, all hydraulic cylinders will become parametric. You can now draw offset of any of these cylinders. And we are going to show you how we can now link the offset of two main cylinders, which are connected with the boom, with one global parameter, because these two cylinders should be moved together. So Ilya has already done it, and when he changed the value, you see that the boom is moved according to assembly constraint we specified before, and in the same way we can animate it. Of course, we will skip the same for other cylinders, but now you have the idea how did we model the kinematics of the moving excavator demonstrated in the movie in the beginning of this session. Okay, it was, by the way, direct kinematics analysis. Now let's consider another important feature of BricsCAD is the possibility to compute mass properties of your product. This excavator is composed of many parts, and every part made of its own material with different physical properties, different density. So you cannot judge about the mass looking just at the volume. You have to compute the total weight taking into account the density of different material, and we can do that with BricsCAD. You see that the total weight is about 36 tons. And what is also important, that this tool allows you to compute center of gravity of this excavator, and now UCS icon is moved to the center of gravity, and you can estimate the stability if your model is well balanced or not. Maybe some design changes are needed. For example, we can rotate the upper platform to 90 degrees and remeasure mass properties to see if this is a stable position or not. And if we switch to the front view, we see that it was even slightly moved to the left, because on the back of this upper platform we have counterweight, as you probably know, which allows you to have a good balance for the excavator. With this tool we can also compute maximal declination angle and write some instruction that you should not put the excavator on more than 30 degrees or so on. Okay, it was just a brief overview of analysis tools in BricsCAD. Let's now move forward and speak more about generation of technical drawings. But first, I propose to take a look on bill of materials of this excavator. We will not take your time to wait when it is generated. We generated it before. It lists all parts and sub-assemblies of this excavator. By the way, it's a new feature of V19, the possibility to generate hierarchical bill of materials. Previously, we generated only parts or assembly level bill of material. Now you can see part number displayed as several numbers divided by a dot, and you can see nested assemblies and sub-assemblies and parts. You can see their quantity, their name, materials, mass, and you can see parameters if needed, and so on. In total, we used over 500 different types of parts and sub-assemblies here, and if you see the total quantity, it's over 3,000. So it's quite complex model. And that's the reason that we will not use it to generate production drawing. We rather take one sub-assembly. But this is very complex sub-assembly as well. This is this drive mechanism, which contains planetary gear transmission inside. Let's see how easily we can create technical drawings for this sub-assembly. We start with generation of base views. In that case, it's a top view or front view and top view. And now, based on these views, we can generate additional drawing views, for example, section view or detail view if needed. In that case, it makes sense to generate a section view because inside we have many parts. It's quite complex, as you saw in the movie in the beginning of this session. And we will see on this section view that every part has its own H angle, which allows you to easily distinguish them. If they are made of different material, we could see different H patterns also applied to it. And also, following international drawing standards, we do not section standard parts. Ilya has just switched to 3D to show you that bearings and bolts are not sectioned. Of course, it's a property, it's a configurable property of every component to be or not to be sectioned. Of course, making such sections is just one way to explore what's inside your assembly. But the most evident way is to create exploded view of the assembly. In other mechanical design software, you create these exploded views by hand. You have to move one part by another. In BricsCAD, it is done automatically now. Ilya has just moved his mouse, and all parts are disassembled, taking into account possible physical collisions between them. So it models a real disassemble sequence. we will generate a drawing view from this, but I just want to say that behind these technologies, there are many other features. We are very limited in time for this general session, so I'm inviting everybody who is interested to attend our in-depth technology session after lunch, when we will show much more about this automatic exploded representation, including animation of disassemble sequence. And now Ilya has just placed this exploded view on the paper space. And one more new feature of BricsCAD V19 is the possibility to annotate all these parts with just one click. You can create balloons in just one click. Previously, you had to create every balloon manually. And also, we supported the possibility to align balloons, in fact, to align any multi-leaders according to any curve. In that case, for example, we can align them along a polyline, and using some sophisticated algorithm, we create a special representation which allows to avoid intersections between leaders. Okay, it was just a brief overview of what we can do in generation of technical drawings for mechanical assemblies. And now I'd like to invite on this stage my colleague Christian Lecomte, who will give you an overview of sheet metal possibilities in BricsCAD Mechanical. Thank you.
Thank you. So, I am Christian Lecomte, and I have been in the business of sheet metal CAD for more than 32 years. That gives you a big clue. I am older than 32. And there is another clue, my accent. Despite my effort, I cannot hide my nationality. So, the question is, why do we need a mechanical CAD, and especially sheet metal CAD? Among reasons, there are three main reasons. First, design. Design part, design assemblies. Second, produce all material and document for manufacturing, prepare for manufacturing. And the third is exchange data. But as Dmitry said, exchange data is not only import-export. It is import and be able to rework. And this is what BricsCAD do very well. All the group and the industrial company has now a multi-CAD environment. And anyway, from the idea to the manufacture, there is many CAD involved. So, first, let's see how to create from scratch. We start from the upper assembly. And you will see that this part, those two parts are missing. So we will create them from scratch. And we create them on the assembly. And we will use the existing part to be sure to fit to the assembly. So first, we create a profile in this direction. We help ourselves with the existing part. And now we will create another profile in the other direction at 90 degrees. So we can also use some point of the assembly and give the dimensions that we need. Okay, this is now how to create the second assembly. You will see that if we make a mistake, for example, for the height, this is not a problem because we will use the trick of combining two extrusion. Then we will finish the first profile in adding a fillet. No, chamfer. I told you. So now, two extrusions, and then we will combine those two extrusions, and we get the solid. But it's solid, it's not sheet metal. Then we will, of course, isolate this solid and cut in two, because the result must be two parts. So we will cut this solid in two parts, and then it's still solid, and we will shell to get something with a constant thickness. And then we will apply our powerful sheet metal features. Then just in clicking, then we have all the bands are created. Automatically, the junctions are created, and we can switch a band to a junction to be accurate. Then we can add on the back 4 new flanges, 5 new flanges, and you see that the meters are created automatically. It's magic. So, and of course, the part can be unfolded. You see, as it is fast. The second part, we will create 2 bands. We choose to create 2 bands, and then we will create automatically all the junction. And you see, it's very important, then we create junction not only on straight line, but on curves. And that's unique. And then we will create also those 3 bands, 3 parts, 3 flanges. Okay, and it's finished. And this can be unfolded. Of course, the big band is recognized automatically as a lofted band, so made step-by-step bending. Of course, you can change if you want, but by default, it's like that. So now we will replace, in the assembly, we will replace the solid by those parts. This assembly now is ready to be manufactured. So we will complete the second goal, produce the document and material for manufacturing. So we will launch the batch application that will examine all the parts, sort the part between sheet metal and non-sheet metal. The sheet metal parts are automatically unfolded. And the system automatically creates folders, different folders, and save the DXF, the result of the unfolding, in the appropriate folder, sorted by thicknesses. So this, the duration of this sequence is 3 minutes. 3 minutes. 3 minutes for this assembly. You can imagine doing that manually. It would be a nightmare. And most of the CAD system today, if they can unfold correctly, do that manually. So another thing I have to insist is that we don't know. At the beginning, I didn't say if the assembly is our assembly or an assembly coming from outside. For us, it's exactly the same. We can do that. This sequence, we can do that with our assembly. We can do that with a step file. That's very important. We don't import a step file just to see. Okay, we can rework and make this complex batch with DWG, BricsCAD file, SolidWorks file, step file, and so on. So we will wait for the result. There are a lot of parts. So you see that's why it takes 3 minutes, 3 minutes and a half. It's time for pause. BricsCAD work for you. Okay, it's no, there's still some so no. I will show you this unfolding. It's very beautiful. Oh. Oh no. You see our two parts. Okay. Now let's see what we get. We get a report with sheet metal parts. All the sheet metal parts are unfolded, and we get also some parts that we call poor sheet metal. Poor sheet metal means that can be sheet metal, but there is a problem. There are a problem to convert or to unfold. Ilya, can you show the unfolding of the cabin, because it's quite. So you see that we have. You see the kind of unfolding, complex unfolding that we do. Okay, come back to the report. And then we have a problem with the part which is a poor sheet metal. This is a good example. So we will open it and see what happened. But if we zoom on the corner, we see that it is not sheet metal. It is just a solid, just a shell. And we will use now our tools, and we'll see that very quickly. We will select all the vertical and tilted lines and transform in junctions. Then you see that now we have junction, and just in clicking on bend, and that's all, the bends will be created automatically. So the junction and the bends, it takes about 2 seconds, maybe 3. So now we will use our smart split command, because we cannot unfold if we don't make those split. Unfortunately, we have to do that 8 times because there are 8 corners. But this is quite quick. and the part, of course, will be unfoldable. This is important. So you see that this part is a part coming from, we don't know. It can be a step, it can be SolidWorks, it can be anything. But in 3 or 4 clicks, plus 8 because of the 8 corners, we create a sheet metal part, correct? And then we can unfold. Okay, we have unfolded the part. So you see that we have completed those 3 goals. First, design. You have seen that as it is quick to design from scratch, just 2 profiles, shell and split at the appropriate corners. Secondly, produce document for manufacturing. This is just like that. You don't have anything to do. BricsCAD works for you. And if there is something in the import model that is not sheet metal, we can rework and transform in sheet metal. And this year, thanks to new features, it's faster than ever. Thank you. I will give word now to Dmitry for the conclusion.
Okay, I planned, in fact, to show you a couple more slides, but I think we have no time, so I'm inviting everybody to attend our in-depth technology session to know more about the product.